Hello everyone, welcome to lecture 31 of the NPTEL course on Riemannian geometry. So this is really we have reached the halfway stage and we have talked about Riemannian metrics, the induced Levi-Civita connection, and then the curvature of Riemannian metrics, and then we also learned how to calculate this curvature tensor for submanifolds of Rn. And then in the last three lectures we learned the proof of the local Gauss-Bonnet theorem, namely the generalization of the sum angle property to curved surfaces. So now we really begin the second part of this course, namely that of metric geometry, where we will introduce notions of geodesics, distance function and so on, and towards the end of the course we will relate these notions back to curvature, right. So we will learn how the distance affects the curvature and vice versa. Alright, so the central notion in the second part is that of geodesics. So I want to introduce that in this lecture. Right, so let me motivate this by way of an example. So let us say I have a surface embedded inside R3, and let us say I have 2 points P and Q, and I want to find the shortest path from P to Q, right. So imagine you are an ant living on this surface, or humans living on earth, and you want to optimize your resources. So you want to find the shortest path to go from a point to another point. So let us say I do find the shortest path and it looks something like this green path. So now suppose gamma is the shortest path, right, and suppose I reparameterize so that the velocity, so that the speed is always 1. Then we know by a standard calculation that if you take the acceleration vector, that is going to be perpendicular to the velocity vector, right. But even so, if you look at the acceleration vector, that may have a component that is orthogonal to the surface and a component that is tangential to the surface, right. So it may not be, it will of course not be tangential to the velocity vector, but it might still be tangential to the surface, right. But then a little bit of thought, with a little bit of thought, it is clear that if you want to really optimize your path, then it better not have anything in the tangential direction to the surface. The point is, if it does have something in the tangential direction, by correcting in that direction, you can actually make the path even shorter, right. So it is clear that for a shortest path, the acceleration vector ought to be perpendicular to the tangent space of M at gamma of t, right. So more intrinsic way, by the way the Levi-Civita connection is defined for embedded surfaces in M, this is equivalent to the statement that the intrinsic acceleration, namely the covariant derivative of gamma dot along gamma, is identically 0, right, because recall that this covariant derivative is precisely the tangential projection of the acceleration vector. So the acceleration vector being perpendicular to the tangent space is equivalent to the statement that dt of gamma dot is identically 0. So this condition is basically called the geodesic condition, okay. So here is a definition. So let us now go back to an arbitrary Riemannian manifold. So let Mg be a Riemannian manifold, okay. So here is a definition. a smooth curve is called a geodesic if dt gamma dot is identically 0. Okay. That is, gamma dot is a parallel vector field along gamma. Okay. Alright, so maybe let me make a couple of remarks. Firstly, if this is identically 0, then this implies that that the speed has to be a constant. So maybe let me write it here. So this implies that the speed has to be identically a constant. Okay, why is that? That's because if you take the derivative of the speed squared, then by the fact that we are dealing with metric connections, this is just twice dt of gamma dot times gamma dot, which is 0 because gamma is a geodesic, right. So gamma dot squared, and hence norm gamma dot is a constant function. Okay, the second point is locally, let us say x1 up to xn are some coordinates on u, and gamma ijk are the corresponding Christoffel symbols. Then the geodesic equation, which is this intrinsic acceleration being identically 0 in terms of these local coordinates, translates to the following equation, that for all k from 1 up to n, you take d squared by dt squared of the kth component of gamma plus gamma ijk of gamma of t times gamma I dot of t gamma j dot of t, this is 0. Okay, and as usual with the Einstein summation convention, you sum over I and j, since those are the repeated indices, right. So the geodesic equation is a second order nonlinear ODE. Okay. All right, and then the third point is that if you are looking at an embedded submanifold, then this being 0 is equivalent to the statement that the acceleration vector is perpendicular to the tangent space at this point at each gamma of t. Okay. So this is useful in sometimes finding out geodesics of embedded Riemannian submanifolds. Okay. All right. So in a natural question is so a question that we would like to address is, given a point P in M and a tangent vector at that point, does there exist a geodesic gamma, let us say from minus epsilon to m, such that gamma of 0 is p and gamma dot of 0 is v, and the answer is indeed yes, and it's in fact unique. Okay, and this is what we will prove in the next lecture. Okay, so so firstly, if you go back to this local equation, it's a second order and it's a nonlinear equation. So second order basically means that you have to in general specify two initial conditions. So the two initial conditions here will be that gamma of 0 is p and gamma dot of 0 is v. Okay, and even so, because it's a nonlinear ODE, you in general expect only local existence. So this is yes, but only a local existence. Okay, unlike say for the parallel transport equation where you had a linear first order ODE. The order wasn't that important, but the main thing was it was a linear ODE, and hence you had a existence of a solution on the entire interval. Here that won't always be possible, so you will only get a local existence result. Anyway, that's for the next lecture. In the rest of this lecture, I would like to explain some examples. Okay, so let us first look at the simplest space, namely geodesics in Rn. So with respect to the standard coordinates, all the Christoffel symbols vanish, right. So the geodesic equation is basically then just equivalent to the second derivative of gamma being 0, which means that one can easily solve this ODE and you get basically linear paths, right. So all geodesics in Rn are straight lines. Okay, right. So this was simple enough. Let us look at the second nicest example of a manifold, namely the sphere. Okay, so one can look at the sphere of radius r, but the discussion is the same. So let me simplify matters and just take the sphere of unit radius. So let me draw a picture. Right, so remember the problem that the question that I posed, that suppose you are given a point, let us just take the point to be a north pole. The sphere is nice and symmetric, so it does not matter what point I start, what point I am looking at. So let us just take the north pole and let us take a initial tangent direction v. Okay, so I want to now find a geodesic with these two initial conditions. Okay, so the idea is to do the following. So one considers this v, and we also have this the n plus first basis direction. Note that the sphere is sitting inside r n plus 1 g r n plus 1. So we have the n plus first direction that is normal to the sphere at n. So what I do is I just consider the plane. So let pi v be the plane containing these two vectors v and the n plus first basis vector and passing through the origin. Okay. So if you look at the intersection of that plane, so I am not terribly good at drawing pictures, but so that is going to be a plane that contains these, and that is going to cut the sphere in a great circle. So the intersection of this plane with the sphere is going to be a great circle. Okay, so or a meridian. So let gamma b be a unit speed parameterization. Okay. So then clearly gamma double dot is perpendicular to gamma dot. So if you look at the sort of velocity vector here, so maybe let me choose another color. So if you look at the velocity, if you look at the velocity vector here, that's clearly going to lie in the plane. Also let's just look at the position vector of gamma of t. So that's the vector obtained by joining the center to the point gamma of t. So note that the position vector, which I will denote by gamma with an arrow, and gamma dot of t and gamma double dot of t are all contained in the plane. Right, obviously because gamma is a curve in the plane, right. So so then because gamma double, I mean a plane is two dimensional, we have three vectors here and two of them are linearly independent. Also these two are linearly independent. So that basically forces gamma double dot to be a multiple of the position vector. Okay, but in particular the position vector itself gives you a normal to the sphere. So in particular this implies that the acceleration vector is perpendicular to the sphere. Okay. So that means that this is a geodesic. Okay. So this means that gamma is a geodesic. Okay. All right. So so as the third example, so in fact once we, so here's a fact. Okay. So in fact these are all the geodesics on the sphere. We can prove this using the uniqueness theorem that I will prove in the next lecture. Okay. All right. So this takes care of two of our model spaces. Let us look at the third, namely the hyperbolic space. Right. So here one can again do something similar. So I am not going to write down the details. So let us say I want to find all the geodesics passing through my pole. Let us say if you want geodesics passing through other points, they look in the picture they look a bit more complicated, but through the pole, let us say I want a geodesic with this as the initial vector, then these are basically just given by these hyperbolas obtained by intersecting. So geodesics are obtained by intersecting the span of again V and this n plus first basis vector with the hyperboloid. Okay. So now sometime back we saw that that the hyperbolic model was isometric to the Poincare ball model and the Poincare upper half. So then naturally if you have geodesics in one Riemannian manifold and if you have an isometric Riemannian manifold, you expect to obtain geodesics in the isometric models, right. So similarly here let us take maybe the case of of the Poincare disk, so the ball of dimension 2. Here the picture of geodesics is very nice. So the geodesics come in two variety, they either are sort of straight lines passing through the origin, or they are circular arcs that are perpendicular to the boundary of the unit disk in this case. Okay, and so the similar thing also works in high dimensional for high dimensional balls. So similarly, one can also look at the upper half space and ask what are the geodesics there. So again, if you translate by this isometry, the geodesics again come in two varieties. They are either sort of straight lines that are perpendicular to, so of course I am extending them beyond this, whereas technically they cannot extend beyond the line. So they are perpendicular to the x axis, which is the boundary of the upper half space, or they are semicircular arcs that are perpendicular. Okay. All right. So this describes geodesics on the upper half space. Let me maybe calculate out another sort of example. I forgot the number I am on, 5. So this is 6, namely cylinders. Okay, so this is a cylinder embedded inside R3. Right, so with the induced metric, which I will denote by GC. So in cylindrical coordinates, theta and z, this metric GC, I think this was a calculation that I did when I introduced Riemannian metrics. This takes the form d theta squared plus dz squared. So at least on this local strip, this is isometric to R2. So geometrically what this is saying is that if you cut open the cylinder, then the Riemannian metric is the same as what you would obtain by cutting open the cylinder and laying it out on a flat plane, right. So then it is natural that, I mean, for Euclidean space we have seen that the geodesics are straight line paths. So it is natural that there should be the analogues of, I mean, you take a straight line path after you unroll this cylinder, you take a straight line path, and then when you close up the cylinder again, this straight line path is basically going to give you a helix. Okay. So geodesics on cylinders are helices. All right. So okay. So maybe let me do one final example. So in all of these examples that we have seen so far, the geodesics seem to last for all time, right. They seem to exist for all time. I mean, of course straight lines last for all time. Take the example of the sphere, the great circles you can keep traversing again and again, that lasts for all time. Similarly for the hyperboloid, the Poincare disk, the right. So actually for the Poincare disk one has to be a bit careful. The point is this goes back to the calculation that we had some point, that if you parameterize with unit speed, then as you approach the boundary the length of your curve actually becomes tends to infinity. So in finite time you cannot actually reach the boundary, right. So this was again a calculation that I had done long time back. Similarly for the upper half space example, that even as you approach the Euclidean boundary, you can't actually reach that boundary in finite time if your curve is unit speed parameterized. Okay. Alright, so now let me give you an example of a very sort of simple example of a Riemannian manifold where the geodesic may not exist for all time. So let us take the unit disk in R2, but with the restriction of the Euclidean metric. So on the unit disk we have the Poincare metric, which we saw in the Poincare disk metric. The geodesics seem to last for all time, but now you just take the Euclidean disk with the Euclidean metric. Now if you start at a point P, the geodesics again have to be straight lines, but now you see that the straight line will hit the boundary in finite time. So in this case geodesics do not last for all time. So informally geodesics, if you have a Riemannian manifold where all geodesics last for all time, it is called a complete manifold. On the other hand, if the geodesics do not last, if there are some geodesics that do not last for all time, then it is called an incomplete manifold. So this notion of completeness will play an important role later on. Alright, so maybe let me end this lecture with the following remark. So this I will leave this as an exercise. So let gamma be a geodesic so let's say gamma from A to B to M, and let phi such that phi is a diffeomorphism. So in other words, I want to reparameterize my curve. So then the reparameterization gamma tilde, which is gamma composed with phi, is a geodesic if and only if phi is a linear function. Okay, so that is a nice sort of exercise for you to work out. Okay. Alright, so maybe I'll stop here. In the next lecture we will talk about this existence and uniqueness theorem that I referred to, and then we will actually move on to the first variation formula, which will formalize this sort of intuitive picture that I drew at the start of this lecture, that this geodesic equation arose out of trying to find the shortest path between 2 points. So this is made formal by this thing called as the first variation formula. Alright, so that's all for this lecture. Thank you for your attention, and I'll see you in the next lecture. Thanks.